Hello everyone, welcome to PrepFusion, and today we will be starting a new subject, that is control system, right? So this will be the lecture 1 of control system. This is a very important and easy subject, and this is a very scoring subject, right? So please do study carefully this and try to solve as many questions as possible, because many students, what they feel is they can score the most marks on this subject only. Okay, so this is very easier to understand also. So let's let's start, right? So first we'll study the basics of control system, right? This is a lecture 1, right? So in this lecture, what we'll study, basically, if you have time, we will study Weber curve method, but if you don't have time, then we will only study these two, right? Firstly, we'll study what is the need of a control system, why do we need control system, and what is the meaning of control system. That is more important. Okay, then we'll basically do few basic Laplace transform of few basic symbols, right? And what is Laplace transform, that also we will understand, right? So first we have to understand why do we study control system, right? Why do we study control system? So first we have to understand this that before designing or implementing anything, right, in our life or anything, any machine you want to implement, anything that you want to design, first we have to validate that system, right? We just can't think, yeah, this is like a fan, and this can rotate like this, and yeah, we will implement this, build this, and then directly we'll put turn that on switch, and we'll directly see whether it is working or not. No, it doesn't work like that. Then it will just waste so much bandwidth and power, right? So before implementing that, right, we have to validate the system, that is it stable or not stable, right? So whether the system is stable or not stable, for that we need control system to analyze. We need to mathematically model the system. For that also, control system helps. All these things we study in control system, right? And stability I have already told. Also we need to see whether the system is observable or not, whether the system is controllable or not. You may say, what is this term observable and what is this term controllable. All these things we'll study in this subject only, right? So don't worry, I'm just saying the importance of control system. If you want to write, you can write, but if you don't want to write, it's okay, because this may not come in gate, but this is just a for practical knowledge purpose and for your semesters and practical engineering purpose, right? So what else do we need control system for? We have to understand, right, how it affects the output response if we make some changes in the system. By system, what do I mean? Let's say we are in a thermal power plant, right? And in a thermal power plant, what do we give the input? We give the input as coal, right? We give input as coal, and what do we get as the output? We get the output as electrical power, right? So and in between some processing is happening, right? The coal is getting processed, and then we are converting it to converting to electrical power, right? So yeah, this in between thing, right, processing, that is the system, right? That is the whole system. So that can also be taken as an example of control system, right? So if we make some changes in the system, right, then how will it affect our output response? That is also important. Obviously, yeah, this is just very complicated example, but we'll do very simple examples only. Okay, so yeah, this is just an analogy to get you understand. Okay, this is one thing. And all these things, after knowing all these things, then we'll design the system, implement the system. Then we'll, if it's stable, if it is controllable, if it is observable, then only we will design the system, and then only we'll use it in practical life, right? So that's the need for control system. Okay, so all these things are needed. Also, so I'm not writing here, just I explained you may write here. Okay, so yeah, okay, let me just write a bit. Okay, so write a little bit so that it may make your notes good. Stable or not, observable or not. Okay, and controllable or not. Okay, so all these things we have to check. Okay, also the how does the, let me write this down like this, how does output response changes with changes in system, changes with system, right? So if we make changes in the system, how does the output response change, right? Okay, so yeah, all these things are needed for studying control system. Now, like in control system, right, control system is a very broader range of subject, but we are only concerned with linear control system. By linear, what do we mean? Okay, by linear, the system, right, the processing thing, whatever it processes from input to output, that part should be linear. Okay, so I will tell you what does linear mean. Okay, first let me write this down. We study linear control system, right? So what does this linear mean? So this means that system, right, should be linear. Okay, system should be linear. So what does this linear mean? So linear means the system should follow the property of homogeneity and superposition. So it should follow two properties: homogeneity and superposition, right? Homogeneity and superposition. Okay, so what does homogeneity mean? Okay, or what does superposition mean? So for example, superposition means if I give some input, right, x1, and I get some output y1. So you give 1, you get 2, and then you give input like say 2 and you get 3. So what should be one? If I now give the output 1 plus 2, then what should be the output? That y1 plus y2, right? That means superposition. So yeah, let me write this. So let me write here only for x1, right? X1, where let's say this is x1 of t, we're getting some output y1 of we're getting some response y1 of t. Now for x2 of t, right, we're getting some output y2 of t. Now if the system is superposition, right, then if I give input as x1t plus x2t, then the output we shall get is y1t plus y2t. Okay, then that is the output. Okay, now what is the what does homogeneity mean? So homogeneity, right, homogeneity. So homogeneity basically means if I give some input, right, x1, and we get some output y1. Now if I give some multiple of that input, let's say 2 times x1, then the output should also be 2 times y1. Then the system follows the principle of homogeneity. So if I give some input x1, we get some output y1. Okay, now if I give some input as k into x1, right, k into x1, what we'll get as output here is k into y1 of t. If we get the output as k into y1 of t, then this follows the principle of homogeneity, right? So yeah, if the system follows principle of homogeneity and superposition, then the system is linear. And if the system is linear, then the control system, right, is linear control system. Then we are limited in this branch, right? We will only study this branch only. Hence you will always see that whatever system that comes up, right, it will always be linear. It will always be linear. Also in next few slides we will understand it will always be time invariant also. Okay, our system will always be LTI. Okay, LTI system, those things only we will study. Okay, one thing is, you don't need to keep this in too much in mind. Just to know all this, right? Don't need to stress that like I'm not understanding. This is not that difficult to understand, but still if you're not understanding, this is not that important. Just things you need to keep in mind and know, like why are you doing this, okay? So that reason I am telling you. Now coming to the main part, right? Now we will study the basics of Laplace transform. This is important, so do focus here. Okay, so like I hope, like if we haven't completed signals yet, then we will I will give you a brief overview of Laplace transform, right? So firstly, let me explain you what is a Laplace transform of a signal. Okay, Laplace transform of a signal. Let me write this in thicker. Laplace transform of signal x of t, right? Like this is basically a mathematical tool to convert the information, right, time domain information into frequency domain information. Okay, so we write this as x of s. Now x is complex frequency. Okay, x is complex frequency. X of t e raised to power minus st dt, right? And what is s? S is equal to sigma plus j omega. So what is sigma? Sigma is the damping factor and omega is the damping frequency. All these things we'll study in the time response chapter. Okay, don't worry, just know for now that s equals to sigma plus j omega. Okay, and this is the Laplace transform of any signal, okay, any time domain signal. So what does Laplace transform do? Some mathematical let me just see, is it recording? Yeah, is it recording? Mathematical tool. A mathematical tool used to get information in frequency domain, right? So it may happen that it is easier to analyze in frequency domain than the time domain. So maybe we want to do the Laplace transform. Okay, so yeah, you will understand why it is easier and what all those things. Okay, so first we have to like remember a few important formulas, right? This should be at your fingertips, right? So firstly, unit step signal. What is the Laplace transform of a unit step signal? Like I hope you know what is a unit step signal, but if you don't know, let me define. Unit step signal is basically equals to 1 for t greater than 0 and equals to 0 for t less than 0. Okay, so yeah, let me define unit step signal. It is basically equals to 1 for t greater than 0 and equals to 0 for t less than 0. Okay, so yeah, this is the basically the unit step signal. Okay, so let me plot the unit step signal here, u of t, right? U of t. So this is 1 only, okay, for t greater than 0, and before that it is 0 only. Okay, it is 0 only. So yeah, this is what a unit step signal is. So like let's do the Laplace transform of this. So I hope you remember the formula, right? This formula is, you have to remember, there is no other option. Okay, so this time on x of t is what? It is u of t. Okay, it is u of t. So also one more thing, like in Laplace also and in our systems also, all the systems, right, all the systems will exist after t equals to 0 only, not before t equals 0. None of the signals won't exist. Why? We'll just understand in next few slides. Okay, so yeah, let me first do the Laplace transform. So x of s, right, x of s will be equals to integration of minus infinity to infinity u of t e raised to power minus this is minus st, right, dt. Okay, this is the Laplace transform. So one thing we know is that u of t, right, it doesn't exist before t equals to 0. So this integration, right, will be 0 up until t equals to 0. So we can write this integration, and after t equals 0 this is 1 only, so we can replace u of t as 1. Okay, so between 0 to infinity this is 1 only and minus st dt. Okay, so now let me just do the simple integration. This is minus e raised to power minus st 0 to infinity. So it is e raised to power, oh, we have 1 by s also, forgot, don't forget the constant, right? We're integrating with respect to time domain. So what do we get? Basically it is e raised to power 0 minus e raised to power infinity divided by s, right? So we get 1 by s. So for unit step signal the Laplace transform is 1 by s. Okay, let me write the formula, right? So Laplace transform of u of t, right, Laplace transform of u of t is basically equals to 1 over s. Okay, so u of t is 1 over s. Now let's do a little like basic simple basic modification, right? So if I multiply u of t, right, if I multiply u of t by a, what will happen? What will change in the Laplace domain? So if I multiply it by a, what will happen? Here we will get a is just a constant, right? A is just a constant, so a will come outside the integration, a will always remain outside this, right? So what will be the our Laplace transform? It will be a by s, right? It will be a by s. So a of t, right? A of t is equal to a by s. Okay, a of t is a by s. So yeah, this is the basically the Laplace transform. Okay, for a of t. So these things I think you are getting along, right? I hope you are understanding. Now one more thing, what will be the Laplace transform of like u of t minus a? What does t minus a mean? So let me just write this. So what does u of t minus a mean, right? So one thing we know that t greater than 0, the whatever inside is this bracket, right? Whatever is inside this bracket, if it is positive, right? If it is positive, then it will be 1. If it is negative, it will be 0, the whole signal. What do you mean by this? Here what do you see? T greater than 0, u of t is 1. T greater than t less than 0, u of t is 0. So this bracket, right? If this bracket, that is t minus a greater than 0, then u of t will be 1, right? So t should be greater than a. For u of t to 1, u of t equals to 1, right? Here t is not greater than 0 for u of t equals to 1, because the inside bracket term is different. This is not t, just this is t minus a. So this whole term has to be greater than 0 for this whole function, right, to be greater to be equal to 1. Okay, this is a unit step function, right? Function. Okay, this is not like a fixed thing that like t greater than 0 it will be only 1. Okay, this is a function, so that's why t greater than 0, this u of t minus 1 will be 1. And before that, right, before that it will be 0 only. So t minus a less than 0, it will be 0 only. So t less than a, so t less than a, it will be 0. T more than a, it will be 1 only. So this one. Okay, and this is u of t minus a, this is u of t minus a, and this is t only. Okay, this is t only. So yeah, this is the graph for this u of t minus a function. Now what will be the Laplace transform of this? So let me write the formula again, right? Let me write this as x dash of s right now. This is minus infinity infinity. This is u of t minus a e raised to power minus st dt, right? E raised to power minus st dt. So now what is the important point to note here is that this is 1 when t equals to a, right? T equals to a. So this t, right, these are the limits of t, right? So when this t equals to a, then it will be 1. Before that a, right, it will be 0. Now this a, right, here a can be negative as well, so this can lie before t equals to 0 as well. So a can be anything. Okay, but here a will come. Why? Because before a, right, before a, from minus infinity u of t minus a, from minus infinity to a, right, equals to, this is equals to 0 only, right? This is equals to 0 only. For you to understand this, I'm not writing this. Okay, that's why before that it will be 0. Our integration will start from a, it will go to infinity, right, dt. Okay, so this is 1 only from a, e raised to power minus st dt. Okay, now what do you get? Minus 1 over s, again e raised to power minus infinity. Like s is there, but like s times infinity is infinity only. But in this case we have minus e raised to power minus as, right? Minus as. Okay, so this goes to 0, right? This goes to 0. So we're left with e raised to power minus as by s. So like what do you observe? That what is, okay, we are not left with slide. So that the Laplace, right, u of t minus 1 is e raised to power minus as by s, right? U of t minus 1 e raised to power minus as by s. Okay, so like now what will be u of t plus a? One thing we observe, normally u of t, what would we get? We get 1 by s. For t minus a, we get a multiple of e raised to power minus as, right? For minus here we get minus. Now for plus, what will you get? Plus. You can prove it for yourself also, that you can understand. Okay, so u of t plus a, what we will get will be e raised to power plus as by s. Now we can derive this as like a trick, right, as a formula. What we can do simply is that, like, time shift in time domain means multiplication by exponential in frequency domain. Okay, so like what does this mean? Okay, this means that, just wait for the bike sound. This means that if, right, our signal is x of t and we have one Laplace transform of x of s, right, then if our signal is shifted, right, if our signal is shifted by x of t minus a, then what will be the Laplace transform of that? It will be the previous Laplace transform only multiplied by exponential. So this time x of s e raised to power minus as, just like here, right, exponential got multiplied by the previous Laplace transform, and if it is plus, then it will be plus as. Just let me write this. Okay, so yeah, this is the unit step function. Now let's do for the unit ramp function, right? So what does a unit ramp mean? I hope you know ramp. It's basically a linear function, right? So how do we explain ramp? So ramp is written as r of t, right? There it was written as u of t. Here it is r of t. It is t times u of t. Okay, t times u of t, right? Side as sigma only. Okay, so what does t times u of t mean? So this means that we have two parts, right? It is equals to t when t is greater than 0, right, greater than equal to 0, because here at t equals to 0 it is defined, but previously unit step, right, t equals to 0, we don't define the unit step function at t equals to 0, right? So we can do a Gibbs phenomena approximation. By that, what we do is, like, the upper and lower limits, we take the average of the upper and lower limits, and it is half as, but we don't know what is the value of unit step function at t equals to 0. Okay, we don't talk about that. We can talk about t equals to 0 plus or t equals to 0 minus. Okay, so yeah, that thing one I wanted to mention, but don't worry, that won't be much of an issue in your examination or something. Okay, just had to mention that. So now here this time function, right, because at t equals to 0, t is multiplied only, so we get 0 as r of t. Now what is like this t less than 0? It is 0 only, right, because u of t is 0 itself, so it doesn't go to negative, right? It doesn't go to negative, so t equals 0. So now what is happening? This is ramp function only. Okay, so what is the slope of this? 1, right? Slope of this is 1. So what is the Laplace transform this? Okay, so what I will do is write the formula directly here. Homework for you is prove it. Okay, prove it. Like I hope you can prove this at least. Some things you should do by yourself. Okay, so what is the Laplace transform of a ramp signal? T of t, basically. It is basically 1 by s square, right? 1 by s square. So now this is 1 by s square. Now what will be the Laplace transform of something a t of u into u of t, basically multiple of that, right? Because a constant getting multiplied, right? So this is the formula. This you have to prove. Okay, this you have to prove. So Laplace transform is a by s square, right? A by s square. So yeah, this is the basic formula. And also, like, one important thing to note here is what is the time shift this time. If I do a time shift, so you may think that I'm time shifting, right? If I do time shifting, let's say t minus a times u of t, t minus a times u of t. So what will be the result? You might say, yeah, some simple exponential will get multiplied, right? Some simple exponential will get multiplied. So it is minus e raised to minus es by square, right? E raised to minus es by square. But is it true? Is it just shifted by t minus a? Everything is shifted by t minus a? No. Here the unit step hasn't been shifted, right? If I mean, like, what is the actual signal? The actual signal is x of t equals to, let me write this in different color, equals to r of t only, right? So r of t has to shift by a for it to be get multiplied by minus a, right? Exponential. So if I do r of t minus a, what do I get? I get t minus a times u of t minus a. So this will be the value of the function for which the Laplace transform will be this, right? But for this it won't be. What will be the Laplace transform of this? Let us solve. Okay, let us solve. So let me delete this because this was just for the explanation. So let me do a big cut here, and let me, what should I do is, let me simplify this, right? Let me break this down. So what is this? T times u of t minus a times u of t. So what do we know? T times u of t, right? T times u of t is what? This one only, right? T times u of t. Sorry for the sneezing. T times u of t is this one only, 1 by square, right? T times u of t is 1 by square. So it is 1 by square. And what is a u of t? What is a u of t? So a u of t, right? A u of t. Basically a u of t is just a constant step function with a multiple, right? As I explained earlier. So it will be a by s, right? So and it is in negative here, so it will be simple minus. So if I do integration, right? If I do integration of this signal, why did I did it? So if I do integration, right? Some this signal is there and minus this. So we can break this down into some Laplace transform of that signal and minus that signal. We can use the principle of superposition right here. So yeah, I hope you understand all those things. So these are very basic points. So this is a by s only, a by s only. Okay, so this is basically the Laplace transform of this signal, right? This signal, not r of t minus a. Now we will do the Laplace transform of r of t minus a, which is simple only, which I already solved. This one will be right. So Laplace transform so what is r of t minus a? It is basically I've already explained you what is r of t minus a. It is, yeah, here t minus a into u of t minus a, right? So now what is the Laplace transform of this? So it is e raised to power minus a s, right? Shifted by a, right? Delayed by a. So also I forgot to explain that if this is minus a, right? Delayed by a. How is it delayed? Here you can see, right? Here you can see that it is delayed. Initially it was coming here t equals 0, but now it is coming t equals a. It is delayed by a. Now if it was plus a, it would have been like ahead by a, right? It would have been ahead by a, but now it is delayed by a. For that condition, that the signal would have come here. Okay, so yeah, that is that. Yeah, delayed by a. So yeah, this will come out as e raised to power minus as by s square only. So now let's do the Laplace transform of another signal. What is that signal? Basically t times u of t minus a this time. Okay, this time the unit step function is changing. Is the Laplace transform for this is e raised to power minus as by s square? No, it isn't, right? It isn't. Okay, for that only it will be. How will I simplify this? One thing that you can do, what we know t minus a into u of t minus a, that Laplace transform we know a into u of t minus a, that Laplace transform also we know. Okay, so we can combine those two. What we can do is write the t as sum of t minus a plus a. So what we will do, t minus a plus a, so times u of t. Now what will be the Laplace transform of this? So again let me break this down. So this is t minus a u of t minus a plus a u of t minus. Okay, So this will be the Laplace transform of this. So yeah, now can I solve this? Can I solve this? Yeah, what is this? This is r of t minus a only, and this is simply like step function shifted by delayed by a, right? And a multiple of a is there, so this is easy for me to solve. So what I will do to find the Laplace transform of this, right? So this will be what? This we just solved. It is e raised to power minus as by s square, right? And this one is easy only, a times e raised to power minus as by s. So s, okay. So this is the Laplace transform of this signal. Okay, so these are just basics. If you know, right, if you know all this, you can skip through this. You can skip through this lecture and watch it in 2x or like very fast. Okay, if you already know this, because I hope like many of you know already this. So I'm explaining this for the students who doesn't know anything, who don't know anything, right? So yeah, now let's come to unit impulse function. So what is impulse function defined as? The definition of impulse function, right? It is like at t equals to 0, right? At t equals 0, it is very large value, okay? It is infinitely large value, and at t equals to like other than 0, it is equals to 0 only. But there is one property of impulse that I will explain, okay? So at t equals 0, this is infinity, this is t not equals 0, this is 0 only, okay? This is 0 only. So the area is 1. So this 1, right, this 1 isn't the magnitude of this impulse, like I mean isn't the magnitude of, at this point, right? It's in the value, it is the area of the impulse. It's represented like this. So unit impulse, area of unit impulse is 1 only, okay? So what is the property? That is basically the area only, that if you integrate over the whole time axis, right, for a unit impulse function, what do we get? The area is 1. Or we don't have to integrate over the whole time axis, we can just integrate just before t equals 0 and just after t equals 0, then also our area will be 1, okay? So okay, so this is our area of the unit impulse. So this is 1 only, okay? This is 1 only. So this is the property property of impulse, okay? Property of impulse. So like yeah, now what is the Laplace transform of this impulse function, right? So let us do that first. So you have to understand this a bit. So Laplace transform of impulse, right? So it is basically minus infinity delta of t e raised to power minus st dt, right? E raised to power minus st dt. So what you have to do is basically find the value at t equals to 0, right? Because this delta of t, right, it only exists at t equals to 0. It only exists at t equals 0. So this is a like property of impulse function, that any signal, right, any signal, if you multiply it with delta of t, right, if you multiply it, this may sound like x only, okay? If you multiply it by delta of t, then what will be the value of the signal? It will be at t equals to 0, x of 0 times delta of t only. Why? Because this delta of t, right, it doesn't exist for any other time. It doesn't exist for any other time. It only exists for t equals to 0 only, right? For any other time it is 0 only. So this x of t has no meaning other than t equals 0. So that's why this becomes x of 0 times delta of t. X of 0 times delta of t. So here what is our x of t? It is e raised to power minus st, right? So what we will do? We'll replace this, right? Delta of t times e raised to power minus 0 dt, okay? Dt. So now like from the property, right, from the property, this is 1 only, from the property of impulse property of impulse, what is this? This is 1 only, this value is 1, okay? So we get this as, okay, let me write this in different pen. This is 1 only, okay, this is 1 only. So our x of s, right, or Laplace transform of delta of t is 1 only. Now let me make a few changes here. Just like what will Laplace transform of a delta of t? Laplace transform of a delta of t, right? It will be simply a only, right? A only, because it is times 1, so it is a only. Okay, now what is the Laplace transform? Delta of t minus a, right? Delta of t minus a, because a is constant only. A is constant only, so a will come outside only, but like t minus a, we have to multiply the exponential, and Laplace transform of delta of t is 1 only, so it will be e raised to power minus as. Okay, so yeah, these are the three very important signals. Okay, unit step, unit ramp, and unit impulse. Now what is the relation between these two? Like one thing you can note here is that Laplace transform of unit impulse is 1. Laplace transform of, I should have done it in other sequence, first unit impulse, then unit step, and then ramp, but okay, fine. Laplace transform of unit step, right? Laplace transform unit step is 1 by s. So there it was 1, now it is 1 by s, so we are dividing it by s, right? Now for unit ramp, what you are doing, we are doing that, we are dividing again by s, we are dividing again by s, right? So yeah, this is the relation. Okay, this is the relation. So let me write the relation between the three fundamental signals, right? These are three fundamental signals. Let me write like this only. Between delta of t, u of t, and delta of t, u of t, and r of t, right? What is the Laplace transform of delta of t, right? It is equals to 1 only. Now what is the Laplace transform of u of t? It is equals to 1 by s only. And what is the Laplace transform of r of t, right? 1 by s square. Now how we can see the analogy here is that we are shifting from here to here, we're multiplying by 1 by s, then we are shifting from here to here, we're multiplying by 1 by s only again. Okay, and if I shift from here to here, right, we're multiplying by s, and if we're shifting from here to here, we're multiplying by s. Like how else can we like relate this also is that this is ramp, right? So the integration of unit step, right, the integration of unit step is ramp only, if you understand that. Integration of unit step is ramp only. Okay, so for integration we multiply 1 over s. Okay, now the differentiation of ramp, right, is unit step only. How? Because the slope is constant, right? Slope is constant, the value is constant, that's why it remains like this only, like a unit step only. So if you want to differentiate a function in time domain, then in frequency domain we have to multiply it by s, right? If you want to integrate a function in time domain, then in frequency domain we have to divide by s. Okay, this we will study, okay, but this is also another important thing also. Also, like another important thing is that just write this down in your notebook. You should like come back to this later on, right? Okay, what is that thing? That this right, this u of t, what we can call like this, from this we are understanding that this is a step, right? So what I can write here is the step response, right? I hope you heard of impulse response somewhere, or if you haven't, don't worry, I will just write it, just note it down, you don't have to understand anything. The step response, right, step response is basically the integration of impulse response, because we're multiplying by 1 by s. Okay, 1 by s, or you can see the analogy from here also, is the integration of impulse response, right? Is integration of impulse response. Okay, now what is how can I write this different manner also? The impulse response, right? impulse response. Like what is impulse response, what is step response, all this you will understand just in a few later slides, not in this lecture, in the next few lectures. Okay, don't worry. Impulse response, just write this down and remember in your head. Okay, is differentiation of the step response, but be careful while using this. Why? I will also explain this with solving a question, right? Step response. Okay, writing here also. Okay, by solving this. Okay, so yeah, this is the this is the step response. Now like one more signal is there, so this just note it down, don't need to like understand. I will explain you in the next few lectures, right? So now let's do the parabolic signal, right? Parabolic signal. So I will not prove the like how it came, but I'll just write down the form, right? What is a parabolic signal? Parabolic signal, p of t, I hope you know, t square by 2 into u of t. Okay, so this is not t square, right? T square by 2. Why? Because we're integrating the ramp, right? If you integrate the ramp, you'll get t square by 2. Okay, t integration t square by 2. That's why it is t square by 2 like this. Okay, so for us to easily get like this 1 by s term, so here what you can simply do is we're simply integrating this, right? Integrating this. So what I will do, multiply in the Laplace domain, I will do multiply by 1 by s for getting the Laplace transform. Okay, as I did here, integrate this and we get r of t. For Laplace domain, what I did, multiply this by 1 by s. So you can prove it also. You have to do, obviously it is homework for you, but I have given you the analogy, right? So what will be the Laplace transform of this? One by s cube, right? 1 by s square was for the ramp, and 1 by s multiplied by 1 by s square, it is 1 by s cube. Okay, 1 by s cube. Okay, so yeah, another thing is sinusoid signal. This is very, very important. Okay, I will not prove it to you, but this is all homework for you. Laplace transform of sine omega naught t. Okay, so omega naught square plus s square, right? Omega naught square plus s square, like I can write this like this also. This is s divided by s square plus omega naught square. So yeah, this is the formula. You should derive it for yourself. Okay, so these are the standard formulas. Okay, so like another important formula is that what is the Laplace transform for an exponential signal? For an exponential signal, so like yeah, Laplace transform for an exponential signal e of t, right? So this one I will prove. Okay, so minus infinity to infinity minus a of t e of t e raised to power minus st dt. Okay, so what is this? Basically like this exponentials, right? The powers will get added up. Okay, so this is e raised to power minus a plus s t u of t dt. Okay, so yeah, what will be this? So basically u of t exists only for t equals to 0, so this integration limits will change, right? Okay, so yeah, like this integration is simply only because this is a constant only. A plus s is like s only. Okay, in the previous case. Okay, so what will it become? 1 by s plus a infinity. This is minus only. Okay, so we get as 1 by s plus a, right? We get 1 by s plus a. So what do we notice here? We notice that yeah, there was some 1 by s term. Okay, 1 by s, but here it is coming as 1 by s plus a. Okay, so just hold on, let me add a new slide. So for e raised to power minus et, right, ut, we are getting 1 by s plus a. But can we relate this with unit step? So if we multiply by exponential, right, the like the Laplace transform shifts by that same amount, right? What do I mean by this? So for simple u of t, right, for simple u of t we had 1 by s, right, but here what happened, we are multiplying it by e raised to power minus at. So what does this become? This becomes s plus a. This becomes s plus a, right? So this thing you have to understand the analogy, right? So if we multiply e raised to power minus at, then this becomes s plus a. Instead of s, this becomes s plus a. Now if I multiply e raised to power at, what will this become? Anyways, this is not stable signal, so this will not come in to the picture. So don't worry, this signal won't come in, just to understand you a bit of Laplace, right? Just to understand you a bit of Laplace. So this will be e raised to power s minus a this time. Minus a, okay. So this thing you have to understand, right? If you multiply a positive exponential, then the like this s, right, it becomes s minus a plus at, then becomes s minus a minus at, this becomes s plus a. This thing, just the analogy, right? Or you can obviously prove it, but this is the analogy. That's how you can remember this, okay? Now what is the damped sinusoid, right? Damped sinusoid, what do you mean by damped sinusoid? More of this we'll study in the time response chapter, okay? So damped sinusoid, right? Damped sinusoid is basically something like this. It is a sinusoid, but it is reducing in its magnitude, right? Reducing in its magnitude. So sin omega t e of t, okay? So what does the graph look like? So first what we will do is draw the envelope of this envelope, right? How to draw this graph, right? So what I will do is t, this is basically the x of t, right? Okay, so this is the envelope, right? What is this? This is basically e raised to power minus at, right? In both positive and negative, because sign is going oscillating between positive and negative, that's why, okay? So this will look something like this, okay? So yeah, this will be the damped sinusoid, okay? So what will be the solution for this? So basically what we can do is, like, one thing we know, right? One thing we know is, we know the Laplace of sin omega naught t, and we know if a signal is multiplied by e raised to power minus at, then just the s, right? S changes to s plus a, right? Here s change to s plus a. So what is the Laplace of sin omega naught t? Laplace of sin omega naught t is omega naught divided by s square plus omega naught square, okay? Now that s square, right, it will change to s plus a, okay? All the other things are constant only. So that's how you derive it. You don't just solve it blindly, okay? You can solve it, you can cross verify, but this is the easier method. This is the less lengthy method, right? So omega naught square, okay? So yeah, this is the basically the Laplace transform of this damped sinusoid. Also one more Laplace transform we need to do, okay? This is the last one, I promise, okay? It is the pulse signal, right? Pulse signal. So let me do the pulse signal here. So what is a pulse signal basically? So pulse signal is basically like this only. It appears for a short amount of time and then it goes away. Also we can see this as a rectangular signal, okay? Rectangular signal. Okay, rectangular signal. So what is x of t equals to? What is x of t equals to? X of t is equals to a e of t minus a minus, like, I hope you can derive this, right? So how does this t minus a comes up? So this won't be t minus a, this will be t plus a, okay? I am doing mistake by myself only. T plus a, because this is early, right? This is coming early by a, so I didn't mention the points here. This is minus a and this is plus a. So if I put t equals to minus a, what does this become? This becomes u of 0. So just after u of 0, this goes up, right? And the value is a here, okay? I'm not writing the graph, okay? Good, I hope you understanding. Just after a plus, minus a plus, right? I mean just after this minus a, right? This becomes a. So that's why this comes into action. But does this one come into action? So let me write this, e is to minus t minus a, right? So this is at t equals to minus a, this is t equals to minus a, this becomes minus 2a, and u of minus 2a is 0 only, because this is negative, right? A is positive, a is greater than 0, okay? A a is greater than 0, but minus a will be less than 0. This thing we have to understand. So like let me write this here. A is greater than 0. If a is greater than 0, minus a will be less than 0. Just take a number, right? 1 is greater than 0, so minus 1 will be obviously negative and 1 will be positive. Okay, just simple. You can just when you are not understanding anything, right, just take examples. Okay, just take examples. So yeah, this is a u of t plus a minus a u of t minus a. Okay, so now what will be the Laplace transform? So we have already done all this. Okay, we have already done all this. So I will directly write this, pause this video and solve it for yourself also. So Laplace transform of x of t is this u of a upon s, and this is minus this is sorry not minus, this is plus a is, right, plus is same sign multiplied in multiplication or explanation in the time domain, then the sign opposes right here, and this is e raised to power minus yes, it is minus yes. Okay, so yeah, this is basically the Laplace transform of all these things. So like this is the pulse transform. Now what we'll do is we'll just understand a few properties. Okay, just understand a few properties that what is the like the differentiation in frequency domain or multiplication by time property, and what is the integration in frequency domain or division in time property. Okay, so these are just two property. You have to like remember in your head all these things. Okay, so in differentiation in frequency domain, right, frequency or multiplication. I'll just explain you what do I mean by this. Okay, multiplication in time domain, right? So now like let's okay, let me check, is it recording or not? Okay, yeah, it is recording. This is also recording, so I don't know like voice is recording well or not. Okay, so multiplication in time domain. So what do you mean by this? Let's say we have one signal x of t. So if its Laplace transform is x of s, now if you multiply this x of t, right, with t itself, t times x of t, this is basically, then if you multiply it by t, then there will be differentiation in the Laplace domain, in the frequency domain. And how will that differentiation look like? It will be multiplied by minus sign dd of s, okay, times x of s, dd of s times x of s. Now you just have to remember this. Okay, if I multiply t to the power of n, then what will be the Laplace transform of that? It will be simply minus 1. Okay, minus 1. Okay, I should write this like, okay, shit, I should write this yeah, like this only. Okay, like this only. So this is minus 1 to the power n dds of n x of s. Okay, so this will be n also, this will be also n. Okay, so we do the nth differentiation of the Laplace transform of the actual x of t, sorry, x of s, like actual x of t, sorry, Laplace transform of actual x of t, then we multiply it by minus 1 to the power n. Okay, now if n is odd, obviously we'll get minus 1, if n is even, we'll get 1 only. Okay, so yeah, this is one property that you guys need to remember, but don't worry, you I will not recommend you to remember, just write this down, just see where it is coming up. Okay, in most cases I hope this won't come up, this will mainly come up in signals and system. Okay, so here just write this down. Okay, you don't need to remember all of a sudden, just write it down, and if this comes up, then go through the notebook and then again recall in your head, and this will automatically get into your head, right? Automatically things will come into your head. Now we'll do is integration in s domain, right, or division by t in time domain. is open, or okay. So like what will be, so again let's take this example, like x of t has Laplace transform of, just ignore the sound outside, okay, it has Laplace transform of x of s. Now if I divide this x of t by t, right, if I divide this x of t by t, then what will happen to the x of s, right? So we will just simply integrate this, right, from s to x of s. So this is like, this is not that important, this doesn't come in anyways because we don't divide by t anyways, okay. So just I have to mention this, okay. So these are the like basically two properties. Now this is the basically the end of this lecture, because this lecture has went on long. What I will do is, we'll do few example problems of Laplace transform in the next lecture, at the start of the next lecture, and then we'll study the wavy curve method, okay. So yeah, thank you for watching.